Hi, in this lecture we're going to see some logic gates, okay, or logic device. So as you see here, this is the symbols of logical gate, okay. So in this lecture we're going to see logic gates. So let's get started. As you see here, this is the NOT gate, okay. This is the symbol of NOT gate. We have here triangle with this small circle over here. So this is a NOT gate. So this is input and this is output. So for the NOT gate, when we have, for example, here 1, the output will become 0. And if we have 0, the output will become 1. Why? Because this is a NOT gate. The circle means not. Okay? Here we have the AND gate. As you see, we have A and B, two inputs. Okay, for the AND gate, we have two inputs and we have output over here. Okay, so here we have the NAND, as you see, NAND gate. Okay, so the NAND gate, we have two inputs and we have output with this small circle. Okay, so this is the OR gate. Okay, we have A and B, so two inputs and we have one input. This is the symbol of OR gate. Here we have NOR gate. Always this circle means NOR, as you see, in circle. We have here circle, we have not. We have here circle, we have NAND. Okay? So here we have the XOR gate. Okay, XOR gate. As you see, the same as OR gate, but we have another symbol here or shape here. Okay, we have two inputs and outputs. So this is XOR gate. And over here we have the XNOR gate. Why? Because we have not here, the circle here. So we have A, B, and we have output. Okay? So NOT gate, AND gate, NAND gate, we have the OR gate, the NOR gate, XOR gate, and the XNOR gate. Okay, so let's go right now to the next slide. So in this slide, we're going to see the same gates with another equivalent symbol. Okay, so for the OR gate, as you see here, we have the OR gate. See, so this is the normal symbol for the OR gate with here we have here A and B, so two inputs. Okay, and here we have output. Okay, so this gate is exactly like this. This symbol equal this symbol. So this is an equivalent symbol. So we have two inputs always here. Also here we have two inputs, we have output, we have output, and instead of this shape we have this rectangle with greater or equal 1. So this is OR gate and this is OR gate. Okay, so here we have AND gate. As you see, this is AND gate. Okay, or let's see first the NOR gate. Okay, we have OR gate and we have here the NOR gate. So the NOR gate always has this small circle. So here also it has this circle. Okay, so the same symbol, this and this is the same symbol. Okay, but for the NOR gate we add this small circle. Okay, so now let's see the AND gate. As you see, we have the AND gate symbol, the normal symbol, and this is another equivalent symbol. Okay, we have two inputs and we have output, and with this AND symbol. Okay, so we have AND gate. For the NAND gate, as you see, so the same symbol as this, exactly the same symbol, but adding this circle. Always this is not. Okay, so we have AND gate and we have NAND gate. As you see, this is circle exactly like this one. Okay, So let's see now the NOT gate. So this is NOT gate. Okay, we have just one output here, and we have the output over here, and we have this NOT circle. Also for this is its shape. We have equal to 1 and this circle. So this is NOT gate equivalent. Okay. Now let's see the XOR gate. As you see here, we have the normal symbol or gate for XOR gate. As you see, we have two input and we have one output. Also here we have two input and we have one output with equal 1. So this is the equivalent symbol. Okay. For the XNOR gate, we have this circle. Okay, we have because we have NOR. Okay. So we have this circle. As you see, we have here circle, we have here circle. So this is XNOR gate and this is XNOR gate. Okay, so we have OR gate, NOR gate, AND gate, NAND gate, MOT gate, and XOR gate and XNOR gate. Okay, so you can use this symbol, okay, or this or this, okay, as you want, but usually we use these symbols. Okay, over here in this slide we have the flip-flops. Okay, as you see, there is a logical gate and there is a flip-flops. Always the flip-flops made of gates or made it by gates, okay, by logic gates. So we have here the D type. So let's erase this. So we have here the D-type flip-flop. As you see, the input is D, okay? And we have two outputs. We have Q and we have Q bar. If Q is 0, Q bar will become 1. If Q is 1, the Q bar will become 0, okay? So D, Q, and Q bar, this is the input for the D-type flip-flop. For data latch flip-flop, so we have the D input and we have enable. Okay, always we have here Q and Q bar. So if Q is 0, Q bar will become 1. If 1, Q bar will become 0. But we have here an activated signal, enable signal. This flip-flop will not work if this enable signal is not present. Okay, so here we have SR flip-flop. We have so two inputs, S and R flip-flop, and we have two outputs, always two outputs. As you see, we have Q and Q1, so S, R, Q, and Q1. The same principle. If Q is 0, Q bar will be 1. If Q is 1, Q bar will be 0. Okay, and here we have the GK. Okay, GK flip-flop and with two output. Okay, this is G and this is K flip-flop, and this is the output. Okay, so this is all about flip-flops. This is an introduction about flip-flops. Okay, so this is the D-type flip-flop, data latch flip-flop with enable signal. We have here SR flip-flop and GK flip-flop. Okay,